So is my voice is lagging?
Slightly.
Okay, let me check. Is it better now?
Yes, sir, I think so.
So look here, this part, that is red mark part, this is nothing but this is your voltage source, and this inductance that has come from your source. So whole thing is now modulus the modulus of the supply. Okay. Someone has to say yes, no. Then how can I know you are listening?
Yes, sir.
Okay. So this is the model of your rectifier, and this diode will be D1, and this is your D2, and this is your D3, and this is your D4. So, and this, what is this? What is this? This one.
Output capacitor.
Output, what is output capacity? What do you mean by output capacity?
Smoothing capacitor, sir.
Yes, this is the filtering capacity to make your output voltage as much as possible to DC, right? And look here, this is the current here. They're mentioning that this is your the rectifier current ID, and all the ripple is supposed to go there, and the DC current should go to the load current should be at this. So this is the general model, and you should know this. Okay, so now let us start this rectifier with, first we can always talk about that resistive load, right? Let me make the screen bigger. Is it bigger?
Yes, sir, it's bigger.
Okay, good. So the first figure there, this is the line frequency. Of course, this is this is the line frequency. This is the line frequency diode rectifier, and here, look here, is there any inductance here?
No, sir. No, sir.
So we have omitted the inductance here. That means LS, that means the source inductance, we have taken 0. We will consider it later, of course, and what is the effect. If you don't forget it, in the 5th semester, I have taught the IUTM. I don't know about the other. Okay, so now this is the resistive load. We have already learned it. So, okay, so when the, let us draw the input voltage. This is omega T, and this is your Vs, this is your Vm. Okay, so if I write down Vs equal to root 2 Vs sin of omega T, then what is the value of Vm? Big value. What is the value of Vm? With respect to here, root 2 Vs, right? So this is Vm means that it is nothing but Vm equal to root 2 Vs. Okay, for the first half cycle, say up to 5. Input voltage, this is your input voltage is positive, right? So if the input voltage is positive, okay, good, this is the positive. So the current should you follow the like this way. The D1, and then it should go like this, and this is coming back here, and it should go back, and it should go back. So this is the current path of your ID. Is it okay?
Yes, sir.
Okay, then your VD, this VD output voltage, VD will be your ID multiplied by R. So what about the wave shape of your current, that would be multiplied by R, and that is your output voltage, right? So since it is the sinusoidal voltage and the resistance is here the know that resistance is scalar quantity. Of course, the current should follow the voltage.
Voltage.
Right, yes. This will be the ID. Okay,
Yes, sir.
okay. I am using the same figure now. Okay, now it is resistive. Let me change that again. Same. I'm now the voltage has changed its direction here. So the current will go this way, this way, this way, this way, this way. Look here, the current will come this way. So now for this, which diodes are working for this 0 to pi?
D3 and D4.
Here.
Sir, D1 and D2.
D1 and D2, sir.
D1, D2. Okay, for the negative half cycle, here for the negative half cycle, we have changed here. I have shown here. We have changed the direction of the voltage, and we see that the current is going this way, this way, this way, this way, this way. So D3 is covered and it is coming back this way. So here the direction of the current IS was here, and if we keep the IS here, so now the IS is negative, right? For the negative.
Yes,
half
sir.
cycle.
Yes.
Okay, but the voltage, the VD equal to, if it is R, so it is still ID R because current is going in the same direction. Am I correct or not? Through your load.
Yes, sir.
So then we can say that, okay, the output voltage will be like this. So, okay, if I now plot it, okay, I can show it in the later figure. Maybe I can clear all this time. Show you. Here. Look here. So, okay, here. If you can you see it?
Yes, sir.
This is your output
Yes, sir.
voltage. This is your output voltage. And the current is in the same direction. And
The screen sharing is gone, sir.
yes, it will come. Has it come back?
Yes.
Okay.
Yes, sir.
Now we have already seen that the output voltage will be like this. This is your pi, this is your twice pi, and this will be say VD. And the output current will be the same wave shape like this. This is your ID. But I have already shown you that the D1 and D2 should be conducting 0 to pi, and D3 and D4 should. So this is your D1 and this is your D2, this is your D3 and this is your D4. And this is your IS, right? Now when D3 and D4 will be conducting, the current is going like this and it is coming back like this. So IS is now, if I plot the IS here, this will be same as your ID. ID equal to exactly same, IS equal to exactly same as ID. But for the negative half second, look, the current has changed its direction, right?
Yes, sir.
So the current will be like this. You got my point?
Yes.
Yes, sir.
That will be wave shape of. Now my question to you as the master's student, what will be the harmonics of your IS? Does it contain any third, second, fourth, fifth, sixth harmonic?
No, sir.
It has the same frequency of the input voltage, right?
Yes, sir. Input voltage.
So total harmonic distortion, did I define it? Did I define it?
Yes, sir. In previous class, sir.
Okay, so look here, we don't have IS1. So actually IS equal to IS1. So our total harmonic distortion is 0. And also look at the power factor. Input, this is the input current and this is the input voltage. This is input current. So what will be the displacement power factor? Displacement angle, cosine of phi 1. What is that? Phi 1, this phi 1 is what? Look,
Sir,
zero,
phi 1 is
right?
0, sir. Yes.
Zero, sir. Yeah.
So
Yeah,
cos
so
theta is equal to 1.
Displacement power factor then equal to 1, right? For
Yes,
the
sir.
resistive load, we don't need to worry about it. So, okay. Let me go to the next here. Okay, so now you look the ratio of the output voltage. So if you want to find out the DC value, what will be the DC value? Do I need to drive it? I have already told you in terms of VS, in terms of VS. And what should be the output DC voltage? Hey,
Sir, the integral of
90.
just 0.9. I have already told you.
so 0.9 VS.
9 PS. Yeah.
0.9 VS or 0.636 VM, right?
Yes.
Okay. And total harmonic distortion we have already got for this resistive load. Equal to 0, displacement power factor is 1, all these things we can say. Okay. Let us move little. Okay. So this is the resistive load, and go back to the figure, the second figure D. This one. Can you see the figure D?
Yes, sir, we can see.
So look here, this resistive load has been replaced by a current source. What does it mean by current source?
Highly inductive load, sir.
Yeah, highly inductive. Highly. Okay, the example should be like if you, since this is the AC to DC converter, if you put a very big DC motor, whose resistance can be 0, but inductance will be very, very high, then the output current will not be like this, whatever we got for the resistive case. Rather than it will have the value of like this. We can study that thing for you from your Haruna Rashid books later. Or I can tell you, you can go through this article. So that will be your wave shape of your output current, which can be taken as a constant, and this constant current is nothing but a current source. Is it clear?
Yes, sir.
Yes, sir.
Let us go down and see. These are not nicely described here. Okay, now here. My voice is breaking or it is okay?
Sir, it is okay.
Good. So this is your input voltage, Vs. This is your phi, this is your phi square. Or in terms of T, this is your T by 2 and this is your capital T. It does not matter, right? Okay. For the rectifier itself, so we have only one Gauss student here, Sanjida.
Yes, sir.
You are the only one Gauss in
No,
this
sir.
course.
Psychafrin Mim is also here.
Okay, she is present or that's not?
Yes, sir, I'm present, sir. Assalamualaikum, sir.
Well, okay. Now, let us start from here.
Let me.
So, okay, if the output current is like this, and let us put ID. Okay, so this is your D1, this is your D2, and this is your D3, and this is your D4. So, if I want you to plot the output current here, ID, What would be the wave shape? ID. What should be the wave shape? I want to plot with respect to omega t a constant current. What should be the wave shape?
Straight line, sir.
Parallel
Horizontal
to
line.
omega t.
Yes, sir.
Parallel to omega t, right?
Yes, sir.
And this value is here. ID. Nadim,
Yes, sir.
you were responding in the same way as you were responding in your undergraduate class.
Sir, is
Thank
it
you,
good
sir.
or bad, sir?
Of course, good.
Thank you, sir.
Of course, good. Of course, good. Why not? Once Sanjita is always keeping silence, was keeping silence. Sabik also was always silent, right? Sabik in the
Yeah.
class.
Yes, sir.
Okay. Now, look here. This is your IS, and this IS will go for the positive half cycle, of course, for this positive half cycle. This IS will go, and will come back here, right? So IS equal to your ID, and if this ID equal to capital ID. So if I now plot IS, then what should be the wave shape for the up to the pi? Hey, tell me from here.
Sir, for IS or ID, sir?
IS, ID, whatever.
Both, sir, both are horizontal to the horizontal line, sir.
Right
Parallel
here,
to
right?
omega t.
Here,
Yes, sir.
this is IS, right?
Yes, sir.
Yes, sir.
Okay, then for the negative half cycle,
It will be
Negative series.
So
negative.
IS should change, but ID will be same.
yeah, it will like
ID
this.
same. IS change.
I should be just reverse, right?
Yes, sir.
Reverse.
Like this. And what is this value? Capital ID is minus ID, right? Yes or not?
Yes,
Yes,
sir.
sir.
Yes, sir.
That has been depicted in your this figure. This figure is your input voltage. Yes. And this is your IS. Okay. You got it or not?
Yes, sir.
And what will be the wave shape of the output voltage? Same as before, right?
Yes, sir.
So this
Both
will be
opposite.
D1 and D2 will be conducting here, and here D3 and D4. And since the you see the zero crossing of the current is at the same pi omega t equal to pi. So and D1 and D2 will be reverse bias, and current is 0, and then of course D1 and D2 will be turned off at omega t equal to pi. And at when the voltage input voltage reverses its direction to negative opposite, then D3 and D4 is ready to conduct, and also D1 and D2 off. So of course there will be no problem. So current shifting from D1 and D2 will be done immediately. You understand it or not?
Yes, sir.
With zero delay, no delay. And also there is no phase shift of your rectangular shape of your IS and VS. VS and IS, there is no phase shift. Up to this, I think you don't have any problem. Can I proceed?
Yes, sir.
Yes, sir.
From I am teaching, say, almost 35, almost 35 years. Still, if I don't take the full rest before starting the class, at least 10 to 15 minutes, I cannot take the class very nice. And that happened today. And I am very, very upset for this one, with all this nonsense thing. So that has been written here. So IS equal to, if you see that, IS equal to ID if PS equal to greater than 0. If IS PS equal to less than 0, that means the negative half cycle, then IS equal to minus ID. Okay. Okay. And let us move further. Because I'm just following the book. So, okay. And since the wave shape of the output voltage will be the same as the resistive, and they have integrated it, and finally they will get here. That will be a 0.9. Okay. So VDO. Why it is written as VDO? D is the output voltage, VDID output or DC. So why they are putting 0 on O? Can anyone tell me why?
Zero phase shift, sir.
LS0.
LS equal to 0.
Sorry.
Who told that?
Average, sir.
Yeah, who told that LS equal to 0? Who? What's your name?
স্যার আশিফুর স্যার ওখানে ওই যে সাবস্ক্রিপ্ট ইয়েতে
Oh, Ashik, you, yes, you are. Okay, yes. So, yeah, that is why they put it VDO, and VDO is equal to 0.9 VSC. Okay? Let's move. That they have here. Question number 510. So we got this one, right? Now, can you see this equation?
Yes, sir.
What is it? Is what it is written there. Fourier analysis of IS, since it is rectangular in shape, the fundamental and the harmonic components have the following RMS value in the idealized case. IS1 equal to 0.9 ID, and ISH, H stands for the harmonics. So for the even harmonics, since the current is symmetric, current is symmetrical over your T axis, so your even harmonics will be 0 for the properties of the Fourier series, and we can find out ISH will be IS1 by H. Right on here. ISH will be IS1 by H. This H is the for this one for the odd harmonic. So, for suppose you want to find out the RMS value of the third harmonic component, that would be IS by 3. H is 3 here. Okay. H has been replaced by 3. You want to find out fifth harmonic, RMS value of the fifth harmonic, then this will be IS1 by 5. You understand it or not?
Yes, sir.
Yes, sir.
Now, this has been proved in the chapter 3 probably, but I can prove it very quickly here. That IS1 will be your 0.9 ID. Okay, you understand it if you have the rectangular wave like this, and if it is, say this is your ID, and if it is capital ID, and if it is minus ID. So when you are trying to find out the RMS value, RMS means the square mean root, right? So you have to square it. If you square it, come like this, and also it come like this, and then if you take the root over here, and it will come again like this. That means ID. So the RMS value of the rectangular wave will be the same as the peak value. You got my point?
Yes, sir.
Yes, sir.
Okay, good. Now, so the input power, if it is lossless, input power must be equal to your output power. Or if it is lossless conversion, there is no loss in your diodes. So input power will be your Vs, Is1 cosine of phi 1. So do you agree with me why I am writing this one? Power will be this. If this is sinusoidal, your current must be sinusoidal. You cannot take the rectangular current to find out the power. So this Is1 is nothing but that. If it is the input voltage and if it is the wave shape of your say, input current Is, is your Vs, then you will get the fundamental value of your current. That means Is1 will have the wave shape like this. That is given in your book. I'll show you just a few moments. So you have to compare this sinusoidal with this sinusoidal. Is1 is fully sinusoidal with the same frequency of Vs. Am I correct or not?
Yes, sir.
So what is the phase difference between Vs and Is1?
0.
So this is 0. So that means cosine phi 1 is equal to 1. So Vs is 1. And output voltage is not, output power will be nothing but PD. That means your VDO multiplied by ID, right? VDO we have already found 0.9 Vs, and ID already we have found, that is your Is. Okay. Now this Vs and this Vs cancel, right?
Yes, sir.
And this is Is equal to ID. We have already proved. Is is nothing but the this is a VDO equal to 0.9 Vs here, and ID, keep it as ID. So this Vs cancel, so we are getting Is1 is equal to 0.9 ID. Is it clear now? This equation, where is the equation? Is it clear? I have proved it, but you can always get it by Fourier series. If you do the Fourier series, you can find out the peak value and divide it by √2. That will, of course, that will give you 0.9 ID. Because, but the Fourier series is very clumsy and cumbersome analysis. So I always prefer to teach my students that okay, the RMS value of the first harmonics current will be 0.9 of your output current. That means the current source or output current, whatever that was flowing through your load. So now it is very easy for you. If you want to find out, say, Is, we got Is1 by H. So put H equal to 3, put here 3, then you know this is your 0.9 ID. That means your that will be your 0.3 ID, right? You got it or not?
Yes, sir.
Hello?
Yes, sir.
Okay. Now total harmonic distortion. We want to find out the total harmonic distortion. What is the formula?
So square root Is square minus Is1 square divided by Is1.
Right? If I put it inside the root, it will be also this one, right?
Yes.
So that we have already found. This is your ID square, and this is 0.9 ID square, and it will be 0.9 ID square. If you do it, and it will come at 48.43%. What is the physical interpretation of this thing? It is 48.43%. Hello.
So 48.43% is second, third harmonics, other harmonics than first harmonics.
This is your pi and this is twice pi, and our input current is now this one. So it is not sinusoidal. We have contaminated our input current, and the power provider, that means utility, is shouting that you have contaminated or distorted my current, and how much? By 48.43%. If it is sinusoidal, like IS1, that has been deviated to your rectangular by this percent. You understand it? What is saying? If it is sinusoidal, what if this kind was sinusoidal, like for the resistive load? What was the total harmonic distortion?
It was 0.
0. Now, since it is rectangular, it has been deviated from the sinusoidal by a factor of 48.43%, that means 0.48%. You got my point?
Yes.
Yes, sir.
Yes, sir.
And the IEEE, they have set a regulation that for any device, this total harmonic distortion should not cross the limit of 6%. That they will not allow to sell this device in the market. If you can design and do that, and they will test it, and if they find that your total harmonic distortion is greater than 6%, they will not give you the clearance to sell it in the market. You got my point?
Yes, sir.
Yes, sir.
Okay, so you have to do something filtering or whatever. Lot of researches are going on to make it. So what will be the input power factor? Since it is not sinusoidal, then we have to find out the input power factor for this one, right? What will be the input power factor? Let us see. Okay, here that I have already described this figure to you, and they have make it IS1 by this one, and when you put this is a normalized value. You understand it or not? I don't know. So if you put H equal to 1, then 1 by S1, and that is the fundamental. So it is 1. So we got it. And if you put S3, it will be your IS1 by H equal to 3. That means 1/3. And this way it is going down. You understand what I say?
Yes.
The higher harmonics are diminishing this way. So we are very much concerned about maybe this third and fifth harmonics. We can neglect other harmonics, and then we have to design our filters so that at least third and fifth harmonics must be eliminated, so that this current will be very much close to your sinusoidal, and your total harmonic distortion will come to less than 6%. These are the basic things. People are doing a lot of researches, but they don't know the basic thing. Okay. And what is the okay? What they have here? This is the displacement power factor. Now, displacement power factor we have already found. This is your input voltage Vs, and this is your what is this?
Fundamental current.
Right. And then what is the different definition of the displacement angle is that angle between the Vs and the fundamental component.
Current. Yes, sir.
Phi1, and this is 0, right?
Yes, sir.
So that is why this is your displacement
Power factor is cos phi.
cosine of Phi1, and Phi1 is 0, so it is, and then power factor, right? Vs is1, then input power factor, that must be equal to your, this is the input voltage, input power, right? 0.9 Vs ID. This is the output power. Input power is equal to output power for the lossless transmission. So this is your, how much? It is your, okay. Okay, let me keep it on here. Okay, then the BS cancel. Then, okay, then this is your IS, and you know that. Then input, keep it here. The rate of side down. So then input power factor is coming as how much? 0.9 IS.
by IS1.
What is going on here? Let me write down here. Yes, IS1. Right. This is your IS. So now, what will be your input power factor then? Yes, what will be your input power factor then? Input power factor is coming as, so these VS cancel, okay? And
So
Right.
0.9 VS divided by IS1, sorry, 0.9 IS divided by IS1 is equal to input power factor.
is it coming 0.9?
Sir,
No,
in
no.
the left hand side we have IS1, sir. On the right hand side we have IS, so they do not get cancelled out.
No.
Input power factor might be once only.
No. Input power factor is the 0.9 here. That's for sure. But let me think how can I drive it? Displacement part power factor.
Sir, we can
IS1.
get the ratio of IS1 and IS from the THD, I guess.
No, but that has not come from here. Yes, IS input. What do they have to do this? What? Okay. And then it will be yes. So, 0.9 yes. Then yes. If I write down this one, is it coming?
IS1 should be IS. IS should be IS1.
This one should be IS1, right?
First one will be IS.
What?
So IS1 equals to ID.
IS1 equal to not ID. IS equal to.
IS equals to ID, yes.
IS equal to ID, yes.
IS1 equals to 0.9 ID.
IS1 is equal to 0.9 ID. Then the both are cancelling into each other, right? Then power factor is coming on. Okay, I'll show you later, okay? Maybe, I don't know. Let me check, okay? Just a moment. Give me a few moments. It is after IS1 in phase with then okay, this is okay. And power factor.
So previously calculated IS1 equals to 0.9 ID, sir.
IS1 equal to
0.9 ID. We already calculated it.
yes, but how they do power factor, input power factor is they're saying that this one by IS1 by IS, right? They're saying that. Is it not? Is it not?
Yes.
Yes.
Yes,
And
sir.
this is one, and then they're putting that here it is 0.9 ID and it is ID. And then
ID.
this side they can't cancel, and they say that, but it must have some
0.9.
logic. There must be some logic. I'll tell you later. Just I don't want to waste the time, but it is this one. This is of course this one, okay? Just give me a few moments. I'm puzzled. Okay. Yes, I can remember now. What is this? This is your volt ampere, right? Yes.
Yes, sir.
So they call it is VS, IS, then the power factor cosine of phi 1. That must be equal to let me check this one. Just hold on. Here. Look here. Look here. Can you see it now?
Yes, sir.
S is the, okay. Note that the current component, the harmonic frequency do not contribute to the average power drawn from the sinusoidal voltage. The apparent power S is the product of the VS and the RMS current. We have to go back to equation number 3.10. Okay, we'll go there. Then the for sinusoidal quantities, then this one will be the VS. Okay, the power factor is the same as in 3.15. We'll go that, and that is this one. Then what they do, this is power factor will be P by S, and this P will be your 0.9 VS ID, which is your IS, and this is your VS and IS. So this VS cancel and this IS cancel, and the power factor is 9. Okay, now we have to see the equation number 3.15 and 3.10. Okay, just remember, going back. Hmm. $3.10, right? Here. The complex power is defined by this, and therefore the magnitude of the complex, which is also called the apparent power, is expressed by this one. That we know, no problem for that one, right? This is very common for your from your power system. Okay, then 15.15. Oh, okay. They have written that the apparent power, that means your apparent power is multiplied by power factor, that must be equal to P. You got my point? This S equal to your V multiplied by, that means VS IS, and power factor will be your okay. They are considering only the input power. Power factor is this one, power factor, input power factor. So input power factor. Then they said that this will be your VS IS1 cosine of phi 1. Now is it okay? This is 1.
Yes, sir.
This is 1. This VS cancel. Sorry, this VS cancel, and this is your 0.9 ID, and this is your ID. So ID cancel. So input power factor is coming as 0.9. You got my point now?
Yes, sir.
Yes, sir.
Yes, sir.
You understand it or not? It's very easy.
Yes, sir.
Yes, sir.
Apparent power multiplied by input power factor, that with respect to sinusoidal VS IS1, then cosine of phi 1, which is displacement power factor. Okay. So now input power factor. So VS cancel. This IS1 is equal to 0.9 ID, and this IS ID. So, and this displacement power factor 1, and then input power factor, this ID and this ID cancel. Input power factor will become as what? Hello,
0.9.
0.9.
0.9, sir.
am I okay or not?
Yes, sir.
Yes, sir.
So I am not making any gozamil.
No, sir.
Abdullah. Hey, Abdullah.
Sir,
Abdullah is sleeping.
no, I'm here.
So you understand what I say? I did not make any fake statement.
No fake statement.
Yes. And I eventually I prove it. Okay.
Yes, sir.
So I told you I am disturbed, totally disturbed. That is why it is going like this.
We can have a break, sir, maybe.
Yeah, that's true. That,
Then you
that is nice. Yeah.
Yes, sir.
It is
Then
9:30 though. Then we can, yeah, let us take 5 minutes break and come back. Let me put some water on my.
yes, sir.
Okay, let me say what happened, because some of you are right here. And so we are going to give a fresher reception on 10th of July. The Assistant Secretary General has already given the recorded portion of his speech. Our Foreign Minister will be present over there. So we are going to submit the student guide. So that needs to be updated in each year. So and I am the chairman for arranging this fresher reception. You are also will be invited to be there for the undergraduate students. So the student guide is there. So the student guide we got today, and it is supposed to be prepared long time before, but they did not prepare it. And when I get it, and I see lot of mistakes. You got my point. Today is already 1st of July. We have the time only, say 1 week. Then I talked with the Vice Chancellor. I send him the student guide, what file, and I asked him, you please make a committee and to go through it to eliminate if there is any error. So sending the register has sent me this Word file, and then that technology, because of the internet, all this thing, I could not send it, and then I from the mobile, and then I see it again in the computer, and then I download that file, and then I again send it, all these things, and then 10 minutes has gone, and then I become puzzled, totally puzzled. You understand?
Yes.
That happened. That happened. So that is why the class is like this. You just give me 5 minutes, and you also take 5 minutes.
Okay, sir.
Okay. Are you with me? Hello.
Yes, sir.
Yes,
Okay,
sir.
let us start. Now we shall consider the LS, right? Effect of
Source inductance.
Can you remember that?
Sir, slightly, sir, not totally.
You have faced the interview.
Yes, sir. But still, sir, these things are very tough, sir.
Very
And
tough.
yes, sir.
Very tough?
Sometimes, yes, sir. Sometimes it feels like very tough, sir.
Okay. So, okay, let's start with the effect of the LS. The first, and also it is known as the current commutation. Current commutation means, I told you when there is no LS in the previous case.
Transfer of currents from one path to another,
Yeah,
sir.
yeah, that we have. If it was like this, and then current was just moving instantaneously. There is no delay, right? Can you remember this? Just few moments
Yes,
ago,
sir.
I told you. This is your IS and this is your BS. But here, if LS is there, then what will happen? We'll study that thing with the half wave rectifier. So this is the main diode and this is the free wheeling diode. So first we will consider LS equal to 0, no LS. Okay, so when the voltage is positive, and of course current is still highly inductive load. So the current will go like this, say from here. Okay, and then this is the input voltage. So this is your IS, and this is D1 will be conducting here, because the current will go this way. Okay, for the positive half cycle. You understand it or not?
Yes, sir.
Hello. Okay. For the negative half cycle, look here from the negative point, if you change the direction, so that is this. So this diode is supposed to stop conducting, and this free wheeling diode will start conducting. And then this IS is what will be this IS then? When this free wheeling diode, if it is open, and this free wheeling diode will conduct for this one, what will be your current IS?
IS will be 0.
Yeah, I see. So look at actually, yeah, it will be like this. So 0 and then, and the output voltage will be, of course, this one, right? Because when this diode will be conducting and it is ideal, and then the voltage across that diode will be what?
0.
0. Then we are getting a 0 voltage. So our output voltage will have the wave shape half wave rectifier, no problem. But now, if we have that LS, what will happen? That we will study, and up to that we will stop. Okay. And I will go to the what is that? Haruna Rashid schools and tell you about that one. Okay, so that has been, they have described it, and then finally, now we will see that if this LS is there, can you see that? If this is your LS,
Yes, sir.
the voltage across is this GL. So for the positive half cycle, describe it here. This is your VS. For the positive half cycle, this D1 is conducting, and then it is going like this. No problem. Good. The current IS is this one, IS is this one. Here. But okay, the current was previous prior to omega t equal to 0, the current was supposed to 0, right? So now when the voltage has gone to negative, so this diode will also conducting, right? This freewheeling diode should start conducting, but the energy storage in this LS will not give you to start immediately, like the current will not build up IS. This is your IS. I am talking about this IS. IS will not go immediately, rather than this diode, because this is the negative half cycle I'm talking about. Here D2 is conducting, right? Negative half cycle.
Yes, sir.
Yes, sir.
D2 was conducting. So if the D2 was conducting, IS should be 0, right? And and here it got the positive voltage, so your D1 is already forward bias, and D2 should be reverse bias, but the building of the current will not be done immediately like this, rather than it will take some time, because current through the LS does not change immediately. Rate of change of current, it will take a time to build up. So it will build up like this. Okay, let us plot this one. This is your say ID1 and this is your say ID2. So okay, ID1 was there. ID1 was there. And then what will happen when the voltage is positive here, this ID2, this is your ID1, sorry. This is ID2 will go to 0, 0, 0 this way, and the ID1 kind will build up like this. And if you add this ID1 and ID2, you will get that ID. ID will be your ID1 plus ID2. You are applying KCL here, Kirchhoff current law. So when there will be LS, then what will happen? The current was the ID2 was there, ID2 current was there, but it will not go to 0 immediately, rather than it takes some time. And also the current building up will go slowly, this one. And always, if you add this ID1 and ID2, you will always get this, the total current through your load. You understand it or not? If don't understand, then I will explain again.
Sir, could you explain one more time?
Okay. Actually, when there was no LS, so okay, if I plot ID1 and say ID2, so this is your say voltage. So when the VS was negative, of course the ID1 will be this, ID2 will be this one, right?
Yes.
So this is 0. And what was the ID1 during this time? 0. And then if there is no LS, and when the voltage is positive, this current ID2 current will immediately go to 0, and the ID1 immediately take over the current. You understand it or not?
Yes, sir.
So it is known as the commutation, from shifting up from one diode to another. It is known as the commutation. So that will be done immediately. But since the LS is there, then what will happen? So the current here, I have already told you, the current is going to 0, but it will not go to 0 immediately, rather than it is losing the time. It is taking some time, because the total current should be ID, right? So ID1 will build up. That means because of this LS change of the current was 0 before your omega t equal to 0, but at omega t equal to 0 plus, you have already got the positive voltage, but the current will not build up immediately, rather than it will take some time. So this delay will be known as the commutation delay. We call it U. This angle U. So U is the angle, right? I'm again explaining here. So the current was here. This is your ID2, and there it is 0, and it is going down, and then the current build up ID1, and that will go like this. Okay. So suppose this one will be 10 ampere. Okay. So what is the current here then? At omega t equal to 0?
It's 10.
10. Okay, it is 10. Here say it is 9. Then what should be the current here, ID1?
So it should be 1.
1. And when this current is ID2 equal to 0, then what will be your current here, ID1?
10.
It will be 10. So if you add this current and this current, you will always get your 10. You understand it or not?
Yes, sir, I understand.
Okay, now again, when this current is falling down, ID1 is falling down, it will not fall immediately, rather than it will take some time. Okay, the current was 0 here, and it will take some time to build up again. So that means during this time, that means during this interval, so both diodes are conducting. Okay, if D2 is conducting, what should be the output voltage?
0, sir.
0. That means during the commutation, you will not get any voltage in your output. You understand it or not?
Yes, sir.
Okay, good. Look here, that has been given nicely here. During this commutation period, so the voltage output voltage will be 0, and here it is come to 0, and then again it will take some time, because this is the, of course, time the voltage should be 0 here because this is negative, and also during this time D2 is conducting. Who got my point?
Yes, sir.
And here not only D2, D1 both are conducting. So during the commutation period, both diodes are conducting, and that is why we will lose this area. We will have to find out this area. What is this area, and what is this commutation angle U? Okay, now I am going back again to your this thing here. Okay, when the during the commutation here, it is showing you the commutation means the shifting of the current from D1 and D2. When the both diodes are conducting, then if you apply the Kirchhoff voltage law here, then what will be the Kirchhoff voltage? The VS should be your VL plus 0, right? This is 0. So VS should be 0. DL equal to your VS, right? And
Yes,
VS
sir.
equal to √2 VS sine of omega t. And this VL is nothing but L DLS, DIS by dt, then √2 VS sine of omega t. Am I correct or not? Then DIS will be your 1 by or LS is here. Then we can write down √2 VS sine of omega t dt. Then we are multiplying both sides by omega. So then we can write down this is your d omega t. Now we are integrating here. So you will integrate between 0 to u because the angle is now operator is angle. Here, what is the operator? Here. What is the current at omega t equal to 0? IS current at omega t equal to 0. Hey, for the positive half cycle. Yeah. IS equal to ID1. What is the current here? It will be built up like this. It will build up like this, and then it will go like this. You got my point? And this is going like this. So what is the current at omega t equal to 0?
Sir, it's 0.
ID.
No. Here omega t equal to 0.
Yeah.
So the output current, sir, ID.
IS.
IS.
Yeah. I told you this is your ID1,
IS
and it is going like this, right?
So it will be 10. So
like this.
if
Here at omega t equal to 0. At omega t equal to 0, what is the current here? At omega t equal to 0, what is the current? Look here, what is the current here?
Sir,
0.
0.
0, sir.
0. Okay, at the end of the commutation, say U. Here, this is your U. What is the current? IS current.
So it's ID.
Maximum, sir.
ID, right?
ID, sir.
It is
Maximum.
ID, right? And then if we complete the integration, this is omega LS ID. And what is this? You are integrating this part, right? You are integrating this one. You are integrating this one, 0 to U. Is it not the area? Integration is what?
So area, yeah.
Area. It is your AU. So then omega LS ID will be your AU. And if you complete the integration, it will come as, let me show you, I am doing this thing. Look here, that has been given nicely here. DL equal to this, and then they have found this, get this one. I have already told you this thing. And then this is the area. This one, this one is the area. Then we want to find this area. What is this area? We already got omega ls ID. Oh. Gone, right?
Yes, sir. Screen sharing is not.
Okay. Come back.
Yes, sir.
So what we are getting, AU, that means look this area, AU equal to omega ls ID, and if you integrate it, root 2 Vs sine of omega t, d of omega t, and 0 to u, then it will be root 2 Vs cosine of omega t minus, and then u0, and then it will come as what? Root 2 Vs cosine u, right?
Cosine u, sir.
Minus, there is a
That's minus, sir, and plus 1.
And that should be your root 2 Vs, right?
Root 2 Vs, yes, sir.
Then if you this one, then it will 1 plus cosine u. Am I correct or not?
So 1 minus cosine u. 1 minus. Yeah.
Okay. Minus cosine u, omega ls ID, and this is your AU, the area you have lost. Yes or not?
Yes, sir.
Okay, so if we don't lost the area, then VD0, what should be for the half wave rectifier? For the full wave rectifier, it is 0.9 Vs. Then for the half wave rectifier, what it should be? 50%, 0.45 Vs, right?
Yes, sir.
Yes, sir.
Okay. And we have lost this area AU. So negative of this area, and you have to take the average. Average will be, because the time period is twice 5. We have to divide by this one, and then this is not this is with your L. VD0 will be only this one, and if you take the effect of ls, that should be, this is AU by twice 5, and AU is nothing but omega ls ID, right?
Yes, sir.
This is the expression. And what is the then by from this one you can write down 1 minus cosine u will be omega ls ID divided by root 2 Vs, right?
Yes, sir.
Cosine of omega u will be 1 minus omega ls ID divided by root 2 Vs. So from this equation you can always find the commutation angle. That means the delay angle, this angle, this angle, this angle. Look here, this angle. You got my point?
Yes, sir. Got it.
Can you
Yes, sir.
remember these things? I have already
Sir,
taught you.
slightly
Yeah,
coming
but-
back, sir.
Yes, sir. Slightly.
Okay, coming back. Okay. That has been given here, and finally they got it. Look here, the equation number. This one. Okay, inshallah, next class we shall start with the full wave rectifier. This is the half wave rectifier we have discussed with ALS, and the full wave rectifier, inshallah, we shall start here. So let me tell you. Okay. Stop. Last one. Haruna Rashid. Okay. So this will be a reading assignment. Okay, here. So if let me. So this is the full wave rectifier with RL load. We call it, actually this is the representation of the DC load. Then D1 and D2 will be conducting for your positive half cycle, and D3 and D4 will be conducting for the negative half cycle. And since there is R and L and also a back EMF, we will get a current not exactly constant current, rather than there is a fluctuation of the current IU. Okay. And with that one, up to the positive half cycle, IS will be the same as the ID. You understand it? You got my point or not?
Yes, sir.
IS will be the same. We remember that, right? IS will be the same as for the positive half cycle. ID, can you remember for the constant kind we have already seen? And
Yes,
for the
sir.
negative half cycle, it will be a mirror replica.
Minus ID.
Okay. Minus ID. Okay.
Yes, sir.
Okay. And then so with that one, they have find out all this expression. You just go through it and try to find out all these things. Okay. This will be a reading assignment. This part. I shall not cover the class rather than to do it. Sanjida. Hello.
Yes, sir.
Sanjita is sleeping. Now,
No, sir.
how many? 27 students. Okay. So I think all are present. So please give me the sheet of the students with roll number. Now your student ID should be available to you. With the student ID, Sabik,
Sir,
please you send the student ID with name to me.
sir,
Ask your friends to send you so you can make a worksheet and then send it to me.
okay,
Will
sir.
you?
Okay, sir, I can do that. Yeah, okay. Sir.
Okay, so we have taken up to today. We have taken 2 classes. Am I correct or not?
Sir, including today, we have taken 3 with the introductory
Oh.
class.
Oh, forget about that.
Okay.
We did not learn anything.
So 2 classes.
Okay,
yeah.
then, yeah, 2 classes. Okay, so everyone will get the attendance of these 2 classes, and from the next, inshallah, I'll see. Because 27 students present means only 1 student are absent. It is absent, so I will find it out.
He was here. He just left right now. I saw him. He was here.
Okay,
We are
so
20 minutes.
okay, all students are here. Okay, thank you very much.
Sir, assalamu alaikum. Sir,